Okay, so I'm going to go ahead and just start because that seems to be the way things work. So I'm going to try to use the Blackboard most of the time today, and maybe all of the time depending on how fast things move. Let me just remind you where we stopped the last time. I gave you this very long history about where we were with neutrino physics, and I try to point it out, I pointed out where we were sort of at the end of the 20th century, where two bad things were happening at the same time. And this is something called the solar neutrino problem and the atmospheric neutrino problem. And they can be very, very easily summarized by saying that if you look at solar neutrinos, that we had a prediction for how many electron neutrinos are produced in the sun, and somehow by the time they got to your detector on the Earth, they were disappearing. And we had very, very strong evidence for that. And again, I want to remind you that this is not a subtle effect. This is an order 1 effect. You expected 10 neutrinos in some units, and you were getting like 3. So it's a very, very big effect. And at the same time, we had the atmospheric neutrinos. And there, if you looked at all the data that we had available at the time, we also had evidence that we were producing a lot of muon neutrinos. And we were also losing them along the way, especially when they propagated a long distance. So this is the picture. And of course, this is in disagreement with other experiments that we had done with neutrinos before. And the main difference between these experiments and those types of experiments was that in the other experiments where everything was working out just fine, the neutrinos were not propagating a very long distance. So whatever seems to be going on appears to be a distance-related effect. So there's a lot of different hypotheses for addressing these different problems. They ranged from very mundane things that maybe our understanding of neutrinos being produced in the atmosphere was wrong in some subtle way, to the fact that maybe we don't understand how to calculate the neutrino fluxes coming from the sun. These explanations were debunked more or less easily as time went by, especially for the atmospheric neutrinos. The robustness of the evidence was very, very strong because it only relied on your atmospheric neutrino flux being isotropic enough that you had this very large up-down asymmetry. So when very mundane explanations failed, then you start appealing to less mundane explanations. And the explanation that people did spend a lot of time on that ends up being the correct explanation, so that's the one that I'll concentrate on, is that somehow these neutrinos can change flavor. That means that if you start out with an electron neutrino beam in the sun, for some reason by the time they get here, some fraction of them have converted into other neutrino flavors. And the same thing is happening with the atmospheric neutrinos. Maybe you start out with a bunch of muon neutrinos, but somehow along the way, they all, or a big fraction of them, get converted into a different type of neutrino. So again, the solution is, or the proposed solution is neutrino flavor change. And again, this turns out to be the right answer. And what I want to tell you before we start talking about the mechanism behind this, which you've all heard about, which is neutrino oscillations, I want to remind you of how it is that we've convinced ourselves, for example, in the case of the solar neutrinos, why what was going on was neutrino flavor change. Okay, and that's the SNO experiment, which I want to tell you a little bit about because it's a very cool experiment. It's also a very important experiment that made a very non-trivial measurement. So this is a SNO experiment. And the idea is to have this very, very, very big tank of heavy water. So it's unusual to think of the fact that the SNO experiment no longer exists because it didn't exist when I was a grad student, so it kind of appeared and then disappeared. But that's how life works, apparently. So the SNO experiment with a very large tank of heavy water, and the idea is that they wanted to try to measure the solar neutrino flux in 3 different ways. And by measuring the flux in 3 different ways, they were going to try to solve this solar neutrino puzzle. And in particular, what they wanted to test was the hypothesis that even though you're producing a bunch of electron neutrinos, a big chunk of them was converting into muon and tau neutrinos by the time they got to the Earth. So that's the model. And the way that you do that is that you must have different ways of detecting your solar neutrino flux that care about what's the flavor composition of the flux. And I will remind you that all the experiments before that, with a small exception of the super K experiment, they were designed in such a way they could see the electron neutrinos very well, but they were blind to the muon and tau neutrinos. That's why this neutrino flavor change hypothesis works. Because if a big chunk of your neutrinos are in a different flavor, and if your detectors are blind to those neutrinos, your detector will conclude that the flux has gone down. So that's the idea. And what the SNO experiment can do is that it can measure neutrinos in 3 different ways, or it could. One way is by a neutrino electron scattering. So you do neutrino electron scattering, so you're hitting this electron here, the electron shows up in your detector, and then you can see that. This is an interesting reaction because all neutrinos know how to do this. However, it turns out that the electron neutrinos know how to do it better than everybody else. And the reason for that is that if you think about how does this process happen, in the case of the electron neutrino, there's an extra Feynman diagram, which is a W exchange, while in the case of the muon and tau neutrinos, you only have the Z exchange. And the effect of that is that a muon or tau neutrino counts as about 15% as an electron neutrino as far as this experiment is concerned. Okay, so that's one way that they would detect the neutrinos. The other way is they would hit this a deuteron. So this is this a proton-neutron bound state. And then, I always forget this, but so the electron neutrino will hit the neutron, and it would give you proton, proton, electron, like that. That sounds right. So that's another mechanism that you could see, and then you could see the electrons that come out of this reaction. Okay, and again, for this process here to happen, you must have an electron neutrino. If you have a muon or a tau neutrino, the energies are low enough that you can't convert a new mu into a muon, and you can certainly not convert a new tau into a tau because there's not enough energy. So this reaction here only allows you to see the reaction if it's an electron neutrino. Finally, the last reaction that they looked at is a pure neutral current reaction. So it's a elastic process like that. So the idea is the neutrino comes in, it hits the deuteron. The deuteron is a loosely bound nucleus, as you probably all know. So it's easy to break it apart. So the neutrino comes in, it hits the deuteron, it remains a neutrino, and it breaks it up into 2. And the key point here is, so I should have said this, here what you observe is the electron. So there's some signal there that looks like an electron. Here what you observe is also the electron, so you see that. These protons are totally useless. They don't leave a signal in your detector. And in this process here, the thing that you can see is the neutron. So the reason for the heavy water was because the heavy water is easy enough to break that you have some non-zero rate for this neutral current reaction. And then you have to be smart and clever and figure out a way of detecting these neutrons. And that's what the experiment managed to do. Okay, I don't want to go into the details of how the experiment worked. There are lots of interesting questions you can ask. For example, how do they separate these electrons from those electrons? I'm not going to tell you what the answer is, but they know how to do that. It has to do with the angular distribution of the electrons that come out and how they're correlated with the direction of the neutrinos that are coming, for example. So the bottom line is that they had all these different ways of measuring the flux of neutrinos coming from the sun, and in all these different reactions, the types of neutrinos that you could detect were, in quotes, different. This one, you only see the electron neutrinos. This one, you see the electron neutrinos with a small contribution from the muon and tau neutrinos. And this one here, you actually get to see all 3 neutrino flavors with the same strength. So that's what they did. And then they made measurements of the flux, the total flux that they would measure. And there's a very, very famous plot, which I can draw, probably. So it kind of looks like this. if you're agnostic about the flavor composition of the neutrinos coming from the sun, you can write down here the flux of electron neutrinos and the flux of muon and tau neutrinos. I'll say something totally obvious, but I should say that, is that you can't tell whether it's a muon or a tau neutrino. This experiment really doesn't care. Muon or taus are the same because the energies are very low. Remember, the typical energies of neutrinos coming from the sun peter out at around 15 MeV. So that's way before the muon mass. So again, this is the experiment. So for example, if you looked at this guy here, well, I think I plotted it in the wrong way, but it's okay. So if you looked at this flux here, you'd make a flux measurement out of this cross-section, and that only measures the nu E flux. So they got some number that looks like this. And then this other measurement here measures mostly the nu E flux with a little contamination from the nu mu and nu tau flux. That means that if you assume that it's all nu mu, you would get some number, but it's possible that it's all nu mu and nu tau, so you would get a corresponding number over here that agrees with the measurement. So you got some, this is not a good drawing. Okay, so let's draw it this way. So you got some band that looks like this. So this is from the charge current measurement, which is this one. This is from the elastic scattering measurement, which is this one. Electron scattering, charge current, neutral current. And then from the neutral current measurement, you don't care what kind of neutrino you have, so this gives you a nice looking curve that looks like this on this plane. And these were the three measurements that they made. And the measurements kind of look like this if you actually look at their results. And the result that they get is such that everybody agrees with, all the three measurements agree with one another if you interpret the model as saying that you have both nu E's, nu mu's, and nu taus coming from the sun. And they meet at a point where the nu mu and the nu tau flux is very, very large. And this ratio here is about 2 to 1. So there's 2 times more nu mu's and nu taus coming from the sun than you have nu E's coming from the sun. Okay, so this is the result of the SNO experiment. What's more impressive about this is that if you look at the calculation of the total flux that's done by this thing called the standard solar model, and you ask what's the total flux if you don't care about the flavor of the neutrino, it actually agrees with this number. So that means that the standard solar model was correct, at least within the error bars that they presented, and somehow the sun can produce a lot of nu mu's and nu taus. Okay, so that's the idea, and this was confirmed experimentally that this hypothesis here was completely correct for the solar neutrinos, that somehow, even though the sun is completely incapable of producing muon and tau neutrinos, nonetheless, by the time the neutrinos get to Earth, 2/3 of your electron-type neutrinos have converted into muon and tau neutrinos. So that's what the SNO experiment did. It's a very clever experiment, and actually this is another Nobel Prize-winning experiment because they've revealed beyond reasonable doubt that neutrinos can change flavor as a function of distance. For the atmospheric neutrinos, the last thing I want to say is if you remember the data that I showed, the information that's important here is the fact that if you looked at the fluxes of, say, nu E's produced in the atmosphere, there was good agreement between data and Monte Carlo. If you looked at the nu mu's that were produced in the atmosphere, there was a strong disagreement when the neutrinos propagated a long distance. So the interpretation for that is that if these muon neutrinos are turning into something else, they're not turning into electron neutrinos, because if they were turning into electron neutrinos, we should see an excess of electron neutrinos. So because we don't see that, the hypothesis that was raised is that these muon neutrinos here were converting into tau neutrinos. And of course, this is a story that everybody must have heard some version of at some point. But this is where we were. So what we want to talk about now is how do you solve this problem? So how do you allow the neutrinos to change flavor? And I'll probably discuss this relatively briefly because everybody has heard about this. But we want to talk about neutrino flavor change. And the only hypothesis we're going to make is that the neutrinos have mass. And it turns out that if you make this hypothesis, and you don't have to add any new interactions to the model, you can explain all of these data. Okay, so this is the massive neutrinos potentially leads to a phenomenon called neutrino oscillations. And what I want to do is to cover this phenomenon a little bit. Yeah? Is there a way to? To get the flavor changed without a mask? So people have explored this possibility, and if you write down vanilla models, it's very complicated because the types of mechanisms that you would invent to allow the neutrinos to change flavor in some dynamical way without having masses, they either had to rely on very interesting non-standard interactions for the neutrinos, which is one way to do it. So basically, the idea is very similar to what the neutrino masses do. In order for the neutrinos to change flavor, you must have two different ways of talking about neutrinos. So you have to talk about neutrinos with regards to, for example, the weak interactions, and that's the electron neutrino, the mu neutrino, and the tau neutrino. And then you must have some other way of describing what a neutrino is. And if those two ways are different, then it's possible that your dynamics can change the neutrino flavor for you. And this is the kind of things that people talked about. One thing that can do that is, for example, if the neutrino has a magnetic moment, that means it talks to magnetic fields. And by talking to the magnetic field, the neutrino could actually change into a neutrino with a different flavor. That's one good example of that. This is not a good example because in that case, the neutrinos also have a mass, probably, because magnetic moments violate chirality. So they prevent, that means that the neutrino mass is no longer protected from the neutrinos are no longer protected from having a mass, which means that they'll get a mass in some order in perturbation theory. A different way to do it is to invent some new interaction, and this new interaction could allow the neutrinos to change flavor along the way, and people also explore this possibility. This is completely ruled out because we've observed the neutrinos changing flavor also in vacuum without any matter along the way, so that hypothesis is also ruled out. Again, the reason doing this without a mass is difficult is this other fact that I mentioned before, which is that if you looked at the atmospheric neutrinos, we have strong evidence that the neutrinos have a sense of time. And if the neutrinos have a sense of time, they must have a mass, or there's something unusual going on in their environment, which is the other possibility. So these are the only two choices. Either they have a mass, or and again, neglecting weird stuff. So if you violate Lorentz invariance, or if you say quantum mechanics is wrong, then you can do whatever you want. But that's not as interesting. Okay, so other questions about this? Yeah?
I think I probably remember one model of neutrino oscillation without neutrino mass. And then neutrino coupled right-hand neutrino have Dirac mass.
Mm-hmm.
But right-hand neutrino have some mixing with each other. But since the center neutrino is massless, but still have some mixing by the right-hand neutrino. I think I remember this case.
So that you have to ask if philosophically this means that the neutrino doesn't have a mass, because you would still have the electron neutrino has some probability of being a massive state. That's what the mixing does.
But if you diagonalize this mass matrix, that is the mass.
There are some massless states, that's correct. But the massive states have a non-zero probability of being measured as an electron muon or tau neutrino.
Sure.
So that's the, okay, that I agree with. And again, people did write down, neutrino oscillations without neutrino masses. There are lots of old papers about this, and I think most of them had something to do with non-standard matter effects, if I remember this correctly. Okay, so let me just remind you of how this works. I mean, I don't know how standard this has become in graduate school these days. It should be very standard, but I'm sure it's not. So the idea is very simple. If you postulate that the neutrinos have mass, then you have two different ways of describing what a neutrino is. And you can question what this means, and if you don't question, then I won't say anything. But the idea is we can talk about, say, the electron neutrino, the muon neutrino, and the tau neutrino. So we know what these states mean. These are the neutrinos that are produced by charge current interactions. Okay, end of story. But now if I say that the neutrinos have a well-defined mass, then I can also label them that way. I can say, here's a neutrino with a certain mass. I can give it a name. And the names that we use are nu1, nu2, and nu3. So here are two proper ways of describing a neutrino state. What's more, these are all the neutrinos that we have. So if you want to describe, so if I tell you that there is a neutrino, and I don't tell you what neutrino it is, you can take a quantum mechanical view of describing this, and you can say that that neutrino is some linear combination of these three things, and you can measure what the probabilities are, so that makes sense in a quantum mechanical way. Or you can also have a linear combination of these three things. So that means that in some sense, this forms a basis for describing neutrino states, and this forms another basis for describing neutrino states, if you want to think about it that way. And the key thing is that once you assume that the neutrinos have a well-defined mass, you can start asking yourself, so what's the relationship between these guys and these guys? And the answer, of course, is that the electron neutrino does not have to be an eigenstate of mass, and the muon neutrino doesn't have to be an eigenstate of mass, and so on and so forth. But the idea is that the thing that we call the electron neutrino is some linear combination of these states. Right? So we say that this looks like some linear combination of these neutrinos with a well-defined mass. The same is true for the muon neutrino, and the same is true for the tau neutrino. Okay, so this is the idea. So the very simple idea, and you could have done that, this is very easy to convince yourself of, is that what we call the electron neutrino is actually a linear combination of neutrinos with a well-defined mass. The muon neutrino is some other linear combination of neutrinos with a well-defined mass, and the tau neutrino also looks like that. Now, I suspect that most of you have heard this story before. One thing which is always important to keep in mind is that this is not different from what we do in the quark sector when we describe the weak interactions. So people sometimes get confused about this. I'm sure you don't, but I will tell you what the answer is anyway. Or the way to think about this, of course, is if you remember in the quark sector, when we talk about the weak interactions, we allow for mixing. And there's an antiquated way of describing mixing, which is to say that in the quark sector, at least for the down quarks, we can talk about the down quark and the strange quark and the bottom quark, but then we can also talk about the weak interaction eigenstates, which are the objects that couple to the up and the charm and the top. And sometimes these are called the D prime and the S prime and the B prime. So I assume everybody knows everything about this. So if this rings a bell, then the nu E is the D prime. And this is like the S prime, and this is like the B prime. These are the eigenstates of the weak interactions. The real particles, the things that we care about, are actually these mass eigenstates, the nu1, the nu2, and the nu3. And of course, these linear combinations that show up here also show up in the case of quarks, and they are the entries of the CKM matrix. Okay? So I assume everybody's very familiar with that. So these U's also form some 3 by 3 unitary matrix, which is not the CKM matrix, but it's some other matrix. And so this U is some unitary matrix. And the idea is that this contains a bunch of new physics parameters that you have to go out and measure. This goes by many, many names. So some people call it the neutrino mixing matrix. Other people call it the leptonic mixing matrix. Some people call it the MNS matrix, just to compete with the CKM matrix. And then the official name, I think, is the PMNS matrix, because they wanted to honor too many people, so you ended up with 4 letters. So, but that's a unitary matrix that describes this mixing phenomenon. And the claim is that by postulating that the neutrinos have different masses, you can explain all of these data. That's the claim. And the way that this works is very simple. And I want to do this relatively quickly because I assume that most of you have heard about this. And I don't want to get caught up in all the funny details that invariably arise because people get confused about quantum mechanics. So quantum mechanics is really hard, so we're not going to talk about that. I am going to give you the cheat description of neutrino oscillations because it works, it's correct, and I will try to tell you what I'm doing as far as cheating is concerned so you can start thinking about it for yourself. So that's my plan. But the idea in principle is very simple. If we go back to the language that we used to describe neutrino oscillations, which is this thing of flavor eigenstates and mass eigenstates, you can ask yourself, what does it mean to be a mass eigenstate? And the language that's most useful for us is to say that the neutrino mass eigenstates are the eigenstates of the free particle Hamiltonian for the neutrino. So that means if you have a neutrino in free space with no forces acting on it, the eigenstates of the free particle Hamiltonian are these mass eigenstates. That's the idea. So that means that if you have a quantum state, which is one of these mass eigenstates, say like neutrino number 1, then its time evolution in space and time is just sort of like a plane wave. So it gets some phase. And that's how it evolves in time. Okay, this is the idea. So that's all we were going to use. And you can already see why this is exciting, because the phase factor that you get as you evolve in space-time is the momentum 4 vector. And of course, these are neutrino mass eigenstates, so they satisfy this dispersion relation here. And this is all that we care about, because when we do experiments, we never ever start with an initial condition that looks like a neutrino mass eigenstate. But we always start with a very different kind of initial condition, which is something like an electron neutrino. So at t equals 0, we have, for example, an electron neutrino, which, as I said, is some linear combination of these neutrino mass eigenstates. So then, as you let time go by, then the electron neutrino is not a Hamiltonian eigenstate. These guys are Hamiltonian eigenstates. They all pick up a phase, but they pick up a different phase. Like that. So this is what you started it. This is at t. This is what your neutrino state looks like. And the thing which is most important, which everybody knows from undergraduate quantum mechanics, is that this is the electron neutrino. This is not. This is some other state. Because again, you have these phase factors which are different for the different components of your neutrino state. So whatever it is that you started out with, you have something else after you've, so if you have this event at x and t equals 0, if you look at the event of detecting the neutrino at some other x and t equals something else, then you have an object there that's not the electron neutrino anymore. Okay? So that's neutrino oscillations. And of course, like I said, all of my neutrino states can be expanded or can be written out in this flavor basis. So for example, if I call this here my neutrino at some space-time position x, then the probability that this thing is an electron neutrino, for example, looks like nu e bracket into this state squared. And this probability is no longer 1. This probability is something else which is less than 1. And that's how neutrino oscillations happen. Okay? So any questions about all of this? Okay, so here's where I made lots of mistakes. The first thing is that I assumed that my initial state is a nu e, which can be written out as a linear superposition of mass eigenstates this way. And then I said that they all nicely evolve in this particular way. And what happens is you're actually doing something very funny because you have a physics process, and I'm telling you that you can emit a coherent superposition of neutrinos with a different mass. Okay, that's the statement. So if you believe that, then you should be very concerned. Because if I'm telling you that I can emit a coherent superposition of neutrinos with a different mass, that seems to violate conservation of energy and momentum. Because if I'm emitting different neutrinos with different masses, but if I am emitting them in a coherent way, there's no way that they can all have the same energy and momentum, because that would violate conservation of energy or momentum or both. So the challenge is what's going on here. And what's going on here is that we're not describing this physics process properly because there's a bunch of uncertainties everywhere. And these are uncertainties of the quantum mechanical type. So you have to allow yourself, and this is in many, many quotes, to take uncertainties in energy and momentum into account when you write down your neutrino state that was produced. So your neutrino is actually produced with some range of momenta and some range of energies. And if you allow for that, then you can end up having these coherent states like that. Okay? So if you never ever thought about this, then pretend you never heard about this from me. But that's usually half of the battle of understanding what's going on here. And people have spent a lot of time thinking about this. And I have a couple of references in the slides that will be available at some point. Okay, so any questions about any of this? So the rest of the story now is to write out what this object here is. And this is where another set of complaints come in, which I will not worry about at all. But I'll just do the standard derivation of what this phase factor looks like. And I worked too hard on this board for some reason. And the approximations that we're going to make are the usual ones, that the neutrinos are ultra-relativistic. So we're going to say that we're going to assume that the neutrino is propagating in one dimension, say in the x direction, or the z direction, whichever is your favorite direction. So we're going to say z is approximately t. These are neutrinos. They have a very large energy compared with what their masses turn out to be. So we're going to make some assumptions that the momentum and the energy are very, very similar. And if you make all of those assumptions, I will leave this as an exercise, you can figure out that what started out as your electron neutrino state, for example, so your neutrino as a function of position, looks like up to an overall phase factor. Okay, so this is the statement. So the idea is I'm only taking the differences in the phases into account. So I'm extracting out an overall phase factor. And the phase differences that the neutrinos acquire, there's an L missing here. Okay, this only made worse. So there's a relative phase difference between those two neutrinos that's proportional to the mass squared divided by 2 times the energy. If you don't like the energy, you can use the momentum. It's the same thing. Okay, so this is the idea. So under these approximations that the neutrinos are moving very fast and that they are detected at some causal point that's a speed of light away from where they were produced, then this is a very good approximation pretending that neutrinos are plane waves of what the neutrino state looks like. Okay? So with this, again, you don't have to believe any of this. A lot of this you can derive for yourself. I do want to mention something very important. There are lots of smart people who have been very confused about this. If you think about this too much, you will also get very confused. There are people who re-derive this and get the wrong answer. There's a lot of debate about this factor of 2. And just trust me, this is right. Okay, so don't But it's an interesting thing to start thinking about if you never thought about how this works in detail. But this is the language that we all talk about. Now, just for completeness, I do want to talk about the standard way, or the standard, I want to derive the standard formula that people talk about very quickly. So this is in this two neutrino world. So if there were only two neutrinos, then this only goes up to two mass eigenstates. Let me call those two neutrinos nu e and nu mu. Then, in this case, I can take my mixing matrix that looks like this. And this is a unitary 2 by 2 matrix. I can parameterize it by one mixing angle. And I plug this in here, and then I can ask questions, including calculating these oscillation probabilities, which we can do. So let me try to do that. That's probably better. And if you do it this way, you can calculate, for example, that PEE looks like 1 minus sine squared 2 theta sine squared delta m squared L over 4E. I don't want to do the algebra for you because, again, this is a fun exercise. If you've never done this before, and if you've never heard about this before, you have certainly solved this problem before. Again, when you take undergraduate quantum mechanics, one of the problems that you must have solved is the discrete two-level system, like a spin in a magnetic field, for example. So you must have solved this problem. And if you start out with an initial condition that's not an eigenstate of the Hamiltonian, that state will evolve exactly according to that formula that's all the way up there. And if you ask what's the probability that I have the same state back again, you do exactly this calculation, and you get exactly this answer, except that the phase factor in that case will go like the energy difference times the time divided by 2 if you choose to write it in this form. So I hope you've all solved this problem. I hope with less emphasis that you remember how to do it. And if you didn't do it, then I invite you to do it. But that's the expression, and the reason I want to write this down is that this allows us to understand how to solve the atmospheric neutrino puzzle really, really easily. Okay, so that's why I have it up there. And of course, this delta m squared is m2 squared minus m1 squared. Okay? So if anybody has any burning questions about this, if anything I said is incorrect, then let me know. So, okay? So now we can stare at this, and the main ingredients are there. So there's a non-zero probability that if you start your life as an electron neutrino and you're measured as an electron neutrino, that probability will be less than 1. On the flip side, the probability that you're born as an electron neutrino and is detected as a muon neutrino starts out at 0, but becomes different from 0. So that means you have this ability of changing your flavor. And we can stare at this, and there's two different types of parameters that are defined in this formula. Some of the parameters have to do with the experiment. So the experiment is how long the neutrinos have gone and what their energies are. So these are things that you can choose when you do your experiment. The other parameters are given to us by nature, including this mixing angle and this difference of the masses squared. So this is what we have to play with. And of course, I can make a plot of this. And it's not a very deep plot, it's just a sine wave. So it looks like this. This is 1. This is some other number, which is not 1, which is not 0. 0 is all the way down here. And whatever this amplitude here is a sine squared of 2 theta. It has to do with this mixing angle. Okay, so how do I explain the data that I have access to? First of all, I have to understand how come I didn't see this phenomenon before. So I did all these other neutrino experiments, and I never saw evidence of this neutrino flavor change. And the reason must be that all the other experiments I was doing, I was actually doing experiments here when the neutrinos didn't have enough time to start changing flavor. And this already starts telling me something about the parameters that I have access to. And in particular, the parameter that I care about is this delta m squared. This is evidence that these delta m squares are small. So that if this phase factor is really small, then this probability is approximately equal to 1. And that's why we never got to see this phenomenon before. Clearly, this has to be wrong when I go to some very long distance. And this is, for example, where the atmospheric neutrinos come in. So, I should have said, OK, it doesn't matter. I'll say this in a different order. So let's talk about the atmospheric neutrinos. So we're going to use that expression there to solve the atmospheric neutrino puzzle. Oh, OK, I'll use it this way. And I'll remind you of what the data looks like. If I look at muon neutrinos with energies around a GeV, then I measure the atmospheric neutrino flux as a function of the zenith angle. So this is cosine of theta. This is -1 and 1. And they expected something that was supposed to go like this, and they see something that kind of goes like this. Okay, so that's what's observed. So these are neutrinos that are coming from above. These are neutrinos that are coming from below. So how do I explain this using neutrino oscillations? The idea is very simple. So for neutrinos that are they're not traveling a very long distance, nothing happens. So that means that those numbers have to be such that nothing is happening. That means that this, for L of order, say 50 kilometers, delta m squared L divided by 4e is very small. So that number is just 1. On the other hand, for neutrinos that are traveling all the way through the Earth, I am losing about half of my neutrinos. So the way that this gets explained is actually very easy. So you look at this oscillation formula. You notice that nothing's happening, nothing's happening, nothing's happening. Then all of a sudden, these two curves deviate by a lot. And then the deviation kind of flattens out, and it doesn't change anymore. That's what this curve is doing. So the way that you explain that is, let's assume that when the neutrinos are traveling all the way through the Earth, this oscillation is actually really fast. So my oscillation phase, delta m squared L over 4e, has changed, has oscillated many, many times by the time you've gotten to L of about the diameter of the Earth. So in that case, my oscillation formula looks approximately like 1 minus sine squared of 2 theta. And then I have this sine squared function that's oscillating very fast. It averages out to about 1/2. So this is what I think my oscillation probability looks like over here. And I want this number here to be 1/2. And what I conclude from this is that if I choose this number here to be 1, then I can fulfill the behavior of my function over here. And I can explain the behavior of my function over here. And the only thing that's left to decide is what's happening in the middle. And what's happening in the middle is that there's going to be a value of L where this argument of the sine function will be changing not too quickly. So I can see more dramatic effects, for example. So I can see a very large transition over here and so on. And there's this, the behavior is changing between nothing happens to the oscillations averaging out somewhere in the middle. So there's some distance where the oscillation length is of the size of the distance that you've traveled, and this here tells you what this delta m squared number is supposed to be. And in the case of the neutrinos produced in the atmosphere, if you look at the data that we have, this is a delta m squared which is about 10 to the minus 3 electron volts squared. Okay? So is that clear? There's a very generic picture that people like to draw in the case of neutrino oscillation experiments. And usually the way it goes is the following. So if you do a neutrino oscillation experiment, your experiment has a certain baseline and a certain characteristic energy for your neutrino beam. So you can then ask yourself, when do I expect to see the oscillations? And the plot that people normally make goes something like this. I put my delta m squared here, and I put my mixing angle over here. So this is one. And the idea is the thing that you're trying to probe goes like 1 minus sine squared of 2 theta times delta m squared L over 4e. You kind of have a couple of interesting regimes that you care about. One is when the delta m squared is really large, such that the delta m squared L over 4e is, so that for the typical values of L and E that you have, the argument of the sine squared is very large. It usually means that within the resolution of your detector, you're going to have many, many oscillations. So that means that the oscillations will average out, and the kind of probability that you're sensitive to will only depend on the mixing angle. So if the mixing angle is large, you have a large effect. If the mixing angle is small, you have a small effect. So if you say that you measure probability greater than something, then for very, very large values of delta m squared, you can say that the sine squared of 2 theta has to be less than something. When the delta m squared values are really small, then you don't get to see anything because the sine squared is 0, basically. But then when the delta m squared L over 4e is just kind of small, then your oscillation probability looks like 1 minus sine squared of 2 theta times the argument of the sine squared. So you get some constant probability curve that kind of looks like this. And then those two curves meet in the middle somewhere. So it kind of looks like that. And here you see a large effect, and here you see a small effect. And for example, a lot of experiments that did not get to see neutrino oscillations for some reason, because they had the wrong baseline, they usually will rule out a region of this parameter space that kind of looks like that. Okay? So this is how we explain this oscillation of the atmospheric neutrinos. Now, the other problem we would like to solve is a solar neutrino problem. And sadly, that problem is not solved using the simple oscillation formula. What happens there is something more complicated, which is the fact that you have to calculate the effect of the neutrinos propagating through a material. And even though the neutrinos don't get absorbed, the important thing to keep in mind is that the neutrino dispersion relation changes. And let me look at the expression here so I don't make a big mistake. And let me just tell you how this works out. All right. And I will also try to do this very quickly. But the idea for this is that the big thing that explains neutrino oscillations is the fact that neutrinos with a well-defined mass have different masses. That's why they pick up these different phases along the way. And this, of course, is intimately related with the fact, we're using the fact that E squared minus P squared equals to M squared. And this is the neutrino dispersion relation. This, of course, comes from, if you remember, the Klein-Gordon equation. And the Klein-Gordon equation comes from the Lagrangian that you started out with. Yeah?
So for this one, we're just using 2 flavors, right?
That's correct, yeah.
So, but that's a simplification. I mean, in reality, some combination is...
Correct, yeah. And I'll come back to this in just a second. But that's correct, yeah. This is a toy model. This toy model works really well. So we will take advantage of that because the real solution will look like this toy model in the right limit, and that will explain why this works so well. Okay, good. So this is what the neutrino dispersion relation is. But let's rewrite the neutrino Lagrangian. So if I write the neutrino Lagrangian, so it has, let me get the signs right. It'll have some nu bar, I del slash nu, and then it has some m term if you want. We're not going to worry about this. But then I can take the weak interactions into account. And in particular, the part of the weak interactions I'm going to care about is the electrons that might be present along the way. So you have an extra term that looks like this. And this looks like nu bar, p left, gamma mu, nu, and then E bar, P left, gamma mu, E. It's actually the other way around. Okay, and this is my Lagrangian if I take into account interactions with electrons for the neutrino. Okay? And it looks horrible now that I erased it with my hand, but it's okay. And again, this is the Fermi interaction that you're familiar with. The only thing that I did is I did a fierce rearrangement of the terms in such a way that I have my neutrino current over here, and I have my electron current over here. So again, what I want to describe is the propagation of a neutrino in a medium that has a bunch of electrons in it. And the way that I interpret that is to say, if I'm propagating in a medium with a bunch of electrons in it, that means that the expectation value of the electron field is not 0. Okay? So I want to do this calculation now. This is not a quantum field theory calculation. I'm just trying to write down the wave equation for the one particle state that's contained in the neutrino wave function, in the neutrino field, if I assume that my electrons have a non-zero background to them. Okay? So let me talk about this very quickly. So it's this term that I care about, the very last term. And the idea is I have this term that looks like E bar gamma mu, then there's a P left E. Okay, and I want to calculate the expectation value of this in a background that has a bunch of electrons in it. Okay, so what does this object look like? And let's forget about the PL for a while, so let's ignore this part. So this is the expectation value of the electron current in a material that has a bunch of electrons in it. So to make life simple, let's pretend I have a lot of electrons at rest. So this object here, if I pick a gamma mu equals I equals 1, 2, or 3, so if I pick mu equals 1, 2, or 3, this is 0, because this is a measurement of how much the electrons are moving around. If I'm in the rest frame of these electrons, they're not moving around at all. So the only non-zero term is this one. Okay, this thing here looks like E bar, not E bar, E dagger E, like that. And this here is just the electron number operator. It's actually the electron number density operator. So this thing here is the electron number density in the medium. Okay? So that means if my neutrinos are propagating through this bunch of electrons that are sitting around, and I ask myself, what's the Lagrangian for that neutrino? Then I have to calculate, the expectation value of this electron operator at the leading order, and that expectation value looks like the electron number density when mu is equal to 0, and it's 0 otherwise. So the Lagrangian that I end up with is this one, where I can replace this electron current by some a constant value. It's not just any constant value, it's a constant value that's only non-zero for the gamma 0 part. So let me replace it over here. So I get a gamma 0 over here. I still haven't told you about the P left. I'll come back to this again. Again, this is not the right answer because there's a P left over here that I didn't take into account. So if this object here is the density of the electrons in the field, if I put a P left here, this is the density of left-handed electrons in my field. That's equal to the total density of electrons divided by 2. Because half of them are left-handed, half of them are right-handed, I only get to see the left-handed ones. Unless somehow my target is polarized or something like that. So I get something that looks like this. So this now, so this cancels out with that, like this. So now I have this funny Lagrangian of the neutrinos propagating in a bunch of electrons. And now I can solve this equation. Or I can find out what's the wave equation for this electron. Or, I'm sorry, what's the wave equation for this neutrino. And it looks like the Dirac equation that you would get out of this Lagrangian with some extra piece that looks like also a propagating piece. So it has, two neutrino fields over here. And the end result of that is that you get a normal propagating wave, except that the neutrino dispersion relation gets modified. So if I ignore the mass, then the neutrino dispersion relation is, instead of E equals P, it becomes E equals P plus this object here. And this is what my modified dispersion relation is for the neutrino. And this is called the matter potential. And the reason it's called a potential is because it looks like a potential energy if you're trying to describe this as, say, a quantum mechanics problem. And I'll come back and I'll mention this again. Okay? So this is very, very grossly speaking how you can understand that. There are more sophisticated ways of understanding this. You can calculate, for example, the neutrino propagator in the presence of this electron background. This is the equivalent of doing some one-loop calculation with a non-trivial background, so you have to learn how to do that. And you also get a modified propagator for the neutrino that has a related dispersion relation that kind of looks like this. So that's almost all I'm going to say about where this comes from, because again, I don't want to dwell on this too much. There's only one last thing I want to mention, is that if you remember what was written here, the origin of this is this current interaction that has to do with the weak interactions. And this dispersion relation here is actually correct for the neutrino state. For the anti-neutrino state, you have to redo the calculation, and you won't be surprised to learn that you get an opposite sign. You get a minus sign instead of a plus sign. That's easy to understand. This is a current interaction. So if we were talking, say, about the electron interacting with a magnetic field, and we wrote down the Dirac equation for an electron in the presence of a classical electric field, we would have gotten a plus or a minus charge for the electron and a plus charge for the positron. And both of these things are coming from the same Lagrangian. So again, this is the same thing. This is a current interaction. So from a current interaction, the neutrino comes out with a certain sign, and the antineutrino comes out with the opposite sign. Okay? So is that more or less clear? All right. So why is this important? So this is saying that when the electron neutrino propagates in a medium that has a bunch of electrons in it, the electron neutrino W boson exchange contribution changes the dispersion relation of the electron neutrino in the material. There's a bunch of other terms which will do something similar. For example, if I had included, say, the Z boson exchange, that would also have looked like a potential, and I should have taken that into account. I should have included, interactions of the neutrinos with the proton and the neutron, for example. And the reason I didn't do any of that is because when you include all of these other effects, they turn out to either cancel out in some magic way, or the same thing impacts the electron neutrino, the muon neutrino, and the tau neutrino in the same way. So the only term that only impacts the electron neutrino is this one, and this is something that changes the dispersion relation of the electron neutrino relative to the dispersion relation of the muon and the tau neutrinos. And by the way, okay, that's fine. I was going to say that the electron neutrino is not a particle because it doesn't have a well-defined mass, so I don't know what the dispersion relation of the electron neutrino means. But I don't want to talk about that, because that just makes life harder. So let's not worry about that. All right. So now that you've understood this part, or at least you've gone through it, the idea is that not only are the dispersion relations of the different mass states different, which leads to oscillation, there's an extra contribution to the dispersion relation of the neutrinos that comes from the fact that they can propagate through matter. So that's an extra phenomenon that also leads to neutrino flavor change in matter being different from neutrino flavor change in vacuum. So we have to take this into account. And in practice, the way that we take this into account is the following. So let me start down here. So what we can do is, in the approximation that I've written down, we can convert this neutrino oscillation problem into a one-dimensional non-relativistic quantum mechanics problem. And that's what we do. So we have a Schrodinger equation that looks like this. So instead of being a derivative with respect to time, we have derivative with respect to distance of a neutrino state is equal to some Hamiltonian acting on the neutrino state back again. So that's the equation that we can solve. And this contains the same information that I used to write down that amplitude all the way up there. So that means I can take that amplitude and I can convert it into a Schrodinger equation. And the reason I do that is that this makes my life easier to include this other modification to the neutrino dispersion relation as well. Because this Hamiltonian here, I can write in this way. It looks like mi squared over 2e times the projection operator into a neutrino mass eigenstate. That looks like this. Plus the matter potential, or it's plus or minus gf and e times the electron neutrino state. That looks like that. And I ran out of room here, so let me not do that. And there's a sum here. So the claim is, the exercise that I did before, you could do again by solving a mock Schrodinger equation that doesn't have this piece to it. And I claim that if you start out with this Hamiltonian, and you have initial conditions that look like an electron neutrino, that your amplitude as a function of distance will look exactly like the thing that I wrote up there. That's the idea. And again, we all know how to solve problems like that. And the advantage of writing things in this way is that I can include this matter effect very, very easily as a modification or as a new term that I add to my Hamiltonian in some sense. Okay? So any questions about that? All right. So no, this is not so bad. Okay. So let me do the following. Just give me 1 second. Okay, so can I use the slides just to not bother you with writing too many things at once? Oh, good. So that worked out. Okay. So having gone through all of this, we can repeat the two-flavor problem again. And the idea is this thing that I just wrote down now. So we have something that looks like a Hamiltonian now. So I have this equation that I would like to solve. And that means that when the neutrinos are propagating through a material, then the equation that you have to solve looks like that, where this A is this matter potential that I try to derive over here on the right-hand side. Okay? Now, from a mathematics point of view, this is in general a really, really messy problem to solve. And the reason it's very messy is that this term over here might depend on the position, or so it depends on the neutrino trajectory. So from a quantum mechanics point of view, it means that you have a time-dependent Hamiltonian. And again, if you remember your basic quantum mechanics class, time-dependent Hamiltonians are really hard to work with. So usually we just give up and forget how to do it. But that means that this is a problem that we may not know how to solve very easily. We can always solve it numerically, of course. There are circumstances where solving this is very, very easy. And one way when solving this problem is very easy is when this number A here is a constant. So when this number A is a constant, then in order to solve this quantum mechanics problem, all that I need to do is to find the eigenvalues and eigenvectors of this modified Hamiltonian and then repeat the oscillation analysis that we did before. So that's what I do over here, and that's why I want to not have to write all of this down. So the idea is if A is a constant, this is the quantum mechanics problem that I want to solve. The solution that I get is the same as the solution that I got before in vacuum, which is that there's some oscillatory probability that you're born as an electron neutrino and are measured as a muon neutrino. And it looks like that. And of course, what changes now is because your Hamiltonian is different, your effective mixing angle is not the same as the mixing angle that you have in vacuum, and the oscillation frequency is not the same as the oscillation frequency that you had before. Again, it's a very, very simple math problem. Because this is a 2 by 2 matrix, we know how to diagonalize that. Again, if it's a 3 by 3 matrix, then the problem is just impossibly hard, so we don't do it. We do it numerically because we're very lazy. 3 by 3 matrices are really hard to diagonalize. You can do perturbation theory often. The problem with doing it that way is that many times the solution is not enlightening. So there are lots of approximate solutions to the 3 by 3 case, which are very interesting. And the challenge is not to do it, but it's to do it in a way that's useful. So what's nice about solving the two flavor problem is that we gain a lot of intuition from it. We would like to also be able to get a lot of intuition from the 3 flavor problem. And we can do that mostly building upon the intuition we developed from the 2 flavor problem. If we want to build some more intuition out of the 3 flavor problem, we need to work harder to get the solution in a form that's useful. And I think we haven't done enough progress there yet, as far as I understand. But lots of people have worked on this problem. But again, for us, the key point is that you have a modified mixing angle, and you have a modified oscillation frequency that depends on this number A. So that means that when the neutrinos propagate in constant matter, the oscillation probability changes. So for example, if the vacuum oscillation looks like this red curve, if you have a non-zero value for A, then you might get an oscillation probability that has a longer wavelength, but also has a bigger amplitude that looks like that. Or you can be the other way around, that the wavelength becomes shorter, but the amplitude also becomes shorter. What's interesting is that if this is a thing that happens for neutrinos, this is the effect that the antineutrinos will see, because this effect depends on the relative sign between the matter potential, which is this thing that's proportional to the electron number density, and if you stare at these expressions here, it's coming from this term over here. So what you care about is the relative sign between A and the delta m squared times cosine of 2 theta. So if this quantity delta m squared times cosine of 2 theta is positive, you get a negative interference here for the electron neutrinos, or for the neutrinos. And if this number here is positive, you get a positive interference for the antineutrinos, or vice versa. So why am I mentioning this? Because this turns out to be a great way of figuring out whether this object over here, delta m squared times cosine of 2 theta, is positive or negative. Okay, and I'll come back to this in just a little bit. But this is the idea. And of course, so you have to learn about these matter effects. And the reason you have to learn about this is the fact that very, very often the neutrinos that you're interested in are propagating through matter. In the case of the sun, this is really dramatic because the interior of the sun is really dense. Sadly, the electron number density that the neutrinos see actually vary very, very quickly with time, or with the propagation distance. So the neutrinos are born in the center of the sun, where it's really dense, and they have to make their way out of the sun, where it's not dense at all. There's actually no electrons there. So it turns out that this is not useful for solving that problem either. So what you have to go back and solve now is a different problem, which is going back to this Hamiltonian here. This is a Hamiltonian where this potential here is changing exponentially with time, or with the distance. And that turns out to be a problem that's not hard to solve if you get lucky. And it turns out we got lucky, so nature was kind to us. And this is a problem that very often you can solve by using what's called the adiabatic approximation. So it has to do with how quickly the potential is changing in units of the time scale of your problem. And if it's not changing very fast, then you can use this thing called the adiabatic approximation. And in the case of solar neutrinos, that turns out to work really well. And I think I have time to talk about this. It's kind of interesting, so I'll talk about it. So again, this is this thing called the MSW effect. And let me just go over the simplified description of this, which is the following. So this is the Hamiltonian, and we want to diagonalize this Hamiltonian here in the center of the sun, or anywhere in the sun, and we can always do that at a fixed value of L. So if I have a fixed value of L, I can always diagonalize this Hamiltonian, and I can pick the eigenvalues and the eigenvectors of that. And in particular, I can plot the eigenvalues of this Hamiltonian here as a function of this parameter A. Now, it turns out that there are two dimension-full parameters in this Hamiltonian. One is this A parameter. The other one is this delta, which is proportional to the neutrino delta m squared over E. So clearly, there are two regimes that I'm interested in. One regime is when A is much bigger than this, and the other regime is when this is much bigger than A. Of course, when A is really small compared to this, then my oscillations just look like vacuum oscillations. So that's easy to understand. The other limit is also really easy to understand, because in the limit where A is much bigger than that, then my Hamiltonian is basically diagonal. I should have said this, but this is the Hamiltonian written in the flavor basis. So this means that when A is very large, the electron neutrino and the muon neutrino are eigenstates of the Hamiltonian. And the eigenvalue, of course, is just A and 0. Okay? So with this information, I can solve the problem. When A is very large, the eigenvalues of my Hamiltonian are either equal to A or some small number. When A is very small, the eigenvalue that I have is this delta. So one eigenvalue is delta, the other one is 0. And the difference between that is delta m squared over 2e. So this is delta m squared over 2e. And this is my eigenstate as a function of A. Okay, so that's not doing anything very sophisticated. I'm just diagonalizing the Hamiltonian as a function of the matter potential. But the interesting thing is the following. When A is really large, not only do I know what the eigenvalues of the Hamiltonian are, but I also know the eigenvectors. And in particular, an electron neutrino is an eigenstate of the Hamiltonian, and it's actually the eigenstate of the Hamiltonian with the large eigenvalue. So that means that all the way up here at very large values of A, the electron neutrino is an eigenstate of the Hamiltonian. And that's exactly my conditions in the center of the sun. So the sun produces an electron neutrino in a very dense environment, and it turns out that the delta m squared and the energy for high enough energy neutrinos is such that the electron neutrino is an eigenstate of the Hamiltonian. Now I need to do the time evolution of this state. And this is where the adiabatic approximation comes in. In the adiabatic approximation, if the approximation is really good, then if you were born an eigenstate of the Hamiltonian, when your parameter A is equal to this number, then the idea is as A changes, you remain an eigenstate of the Hamiltonian forever. So the idea is if you're born an electron neutrino, you were an eigenstate of the Hamiltonian when A is really large, and you stay that way forever, including as A changes. So you're born over here, and then you exit the sun as this eigenstate of the Hamiltonian. And this happens to be the heavy eigenstate of the Hamiltonian. So you have this magic phenomenon, which you also learn in basic quantum mechanics, that you are born an eigenstate of the Hamiltonian, and you exit the sun also as an eigenstate of the Hamiltonian, but it's a very, very different state. But you've stayed an eigenstate of the Hamiltonian throughout. Okay? So this is the idea, and this is really exciting because it tells you that neutrinos born in the center of the sun, if their energies are high enough, exit the sun as mass eigenstates, because these are the eigenstates of the Hamiltonian in vacuum. This means that because of the matter effects, the sun turns out to be an emitter of neutrino mass eigenstates, not electron neutrinos. They actually emit mass eigenstates. And for the most part, they emit neutrino number 2, or the heavy neutrino, in this two-flavor approximation. Okay? So this is the zeroth order approximation to the problem. Life is a little bit more exciting, but not much more exciting. It turns out that there's a probability that the electron neutrino is also born as the low mass eigenstate. So it has a non-zero probability of exiting the sun as a nu 1. And also, there's a non-zero probability that you violate the adiabatic approximation. So it's possible that you're born over here, and then as you're propagating out of the sun, you get over here, and then you jump to the other line, and then you stay and you move along the different line. Okay? So you can take all of that into account. And this is what's explained here. I don't care about this part. And it turns out that this is the oscillation probability that you see of neutrinos coming from the sun. And let me explain this curve, which is very easy to explain. Okay? Remember the numbers that we were fighting off in order to figure out the behavior of my system were delta m squared over E versus this matter potential. And the matter potential that I care about is the matter potential in the center of the sun when the neutrinos are born. So the statement is, when the energy is very high, delta m squared over E is very small. So the matter potential wins. That means that the neutrinos are exiting the sun as a mass eigenstates. And in particular, they're exiting the sun as a mass eigenstate, which is the heaviest one. Okay? So that means that for high energies, the probability that I get an electron neutrino at the Earth is the probability that at that particular mass eigenstate is measured as an electron neutrino, and that's a constant. That's some number between 0 and 1. And if I want to explain the neutrino data from SNO, then I have to pick this number here to be about 1/3. And I can do that. I can look at the opposite limit, which is when the energy is very small. So when the energy is very small, then the matter potential inside of the sun is irrelevant. It doesn't matter. So I only have just standard vacuum oscillations. So this is what you get over here. This is an unfortunate plot. Forget about this term. This is the average vacuum oscillations that I wrote down before. So it's 1 minus 1/2 sine squared of 2 times the mixing angle. I've already picked this mixing angle here to be about 1/3. So this number here turns out to be a little bit bigger than 1/2. So this is the behavior at very small energy for the solar neutrinos. This is at very high energy for the solar neutrinos. Something happens in the middle between this guy being bigger than this or the other way around. And there's some behavior in the middle that looks like this. So this is how solar neutrinos oscillate. Sadly, this is the oldest problem, and it's the one that takes the longest to explain how you solve that. These are the data, by the way. If you measure the survival probability of electron neutrinos as a function of energy coming from the sun, you get these points over here from a collection of very heroic solar neutrino experiments. And the solution, this large mixing angle solution, turns out to be this blue line here. And here's the phenomenon when the matter potential is very important. And here's the region where the matter potential is not very important. And you have this shape that I explained qualitatively in the previous picture. Okay? So this works really well. The other curves in this plot are crazy ideas that also work pretty well. So we're not going to talk about that. Okay? So this is then how you solve the solar neutrino problem, and this is how you solve the atmospheric neutrino problem. I want to skip this for the sake of time, but I do want to summarize then what the situation is in terms of what we've learned by doing these two-flavor analyses. Okay? The idea is very simple. So if I do a two-flavor analysis, the solar neutrinos require a delta m squared of about 10 to the minus 4 electron volts squared, and a mixing parameter which is about 1/3. So sine squared theta is about 1/3. And it's electron neutrinos oscillating into some linear combination of nu mu and nu tau. For the atmospheric neutrinos, I want to do nu mu to nu tau oscillations. Remember, I needed sine squared of 2 theta to be 1, so sine squared theta is about 1/2. And I needed a delta m squared of 10 to the minus 3. There's another piece of information that I will also talk about very quickly, which is the following. Let's see, how do I want to talk about that? So let me not talk about this for a second. But this is what we knew for a very, very long time. And this is the information that we can use in order to actually solve the problem for Rio by using three-flavor oscillations, which I think is what I do in the next slide. So how do I want to do this? So let me try to do this in words because this is going to work out. Well, let me do it over here. So this is the Rio problem. I have this 3x3 matrix. Remember, I have two different oscillation frequencies that I care about. One is 10 to the minus 4. The other one is 10 to the minus 3. Remember, I only care about the differences of the neutrino masses squared. I only have 3 neutrinos. If I need two different frequencies in my problem, then these are the only two frequencies I can get. Because the third frequency, or the third difference between the neutrino masses squared, is over-constrained by the fact that you already know two of the differences of the masses squared. Okay, so that's kind of an obvious statement. And I can explain that if that didn't make sense. So one is 10 to the minus 4, the other one is 10 to the minus 3. This is my mixing matrix. It's a 3x3 mixing matrix. And now I have to, first of all, properly parameterize the matrix. And also I can try to ask myself if it's possible to to pick the right values of all of these numbers over here in order to explain all of these phenomena at the same time. Okay, so this is the goal. And the first thing that I want to talk about is how do we parameterize this matrix? And the way that we do this is just like we do the CKM matrix. It turns out that for the sake of doing neutrino oscillation experiments, you can parameterize this matrix with 3 angles and a phase. The 3 angles are like the Euler angles that you learn in classical mechanics. The phase is like the CKM phase that you learn in particle physics. And this is how we choose the angles. So one angle is the ratio of those two numbers here. So tangent squared of one angle is the ratio of those two guys. Tangent squared of the other angle is the ratio of those two guys. Then there's a third angle that's the sine of the angle is this guy here. And then there's a complex phase that lives here, 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 and here. Everything else you can determine by unitarity. That's actually not true. There are a bunch of ambiguous signs that you have to pick along the way. But if you're careful, you can probably do it. Okay? So this then is step number 1. So these are the parameters that we have available. Step number 2 is I have to tell you who is neutrino number 1, who's neutrino number 2, and who's neutrino number 3. Otherwise, this relationship between my bases is ambiguous. So hopefully you appreciate that. So, we didn't talk about this, but now's a good time to do it. You know who's the electron neutrino, you know who's the muon neutrino, and you know who's the tau neutrino. They are unambiguously defined. Now I want to talk about neutrino number 1, neutrino number 2, and neutrino number 3. I better be able to define those guys unambiguously as well, and I haven't done that yet. If I knew what the masses were, I would not be asking this question, because neutrino number 1 would have mass 1, and neutrino number 2 would have mass 2, and neutrino number 3 would have mass 3. That would be an unambiguous definition of what those guys are. Sadly, I don't know what the masses are, so that means I have to work harder. So the way that we do it is we define the neutrinos relative to one another in terms of how their masses are. Okay? So we have 3 masses. They're all different. So the definition I pick is the following. So remember, I measure the differences of the masses squared. One difference is big, 10 to the minus 3 electron volts. The other one is small, 10 to the minus 4 electron volts. So all of this is nice. And you can ask yourself, what do these masses look like? And they kind of look like this if you ask how are they ordered. So in mass squared, I have a mass difference that's very small. So this is mass squared 1, mass squared 2, or this is 1 mass squared, the other mass squared. And here's what the third mass squared looks like. Except that this is not the only logical possibility. The masses squared can also be ordered like this. And again, all that I know is that this distance here is 10 to the minus 3 electron volts squared, and this distance here is 10 to the minus 4 electron volts squared. And I could have drawn the picture this way, and the physics can't tell this picture from that picture. So that's a question that we're still trying to figure out. Okay, so so now I'm prepared to define neutrino 1s, 2, and 3. And the way that we define them is the following. We look at the mass splitting that's the smallest, and the guy at the bottom is neutrino number 1, and the guy at the top is neutrino number 2. That's my definition. And then neutrino number 3 is whomever is left over. So this is neutrino number 3, or this is neutrino number 3. This is my definition of what the neutrino states are. Once I make this definition, then I can make sense out of what these elements of the mixing matrix look like. This is an unusual definition that you would not have made if you didn't know any better, because it's a little bit cumbersome. You know, if I told you that I have 3 mass eigenstates, everybody would have said, you know, let's make the lightest one neutrino number 1, the second lightest one neutrino number 2, and the heaviest one neutrino number 3, and let's be done with it. And we could have done that, but the reason we don't do it that way is because of this ambiguity here. These 2 pictures are possible given all the data that we have access to, and if I had stuck to the definition that I've just said, you know, this here would have been 1, 2, 3, and this here would have been 1, 2, 3, and there's nothing wrong with that. The problem with doing it this way would be that if the picture looked like the thing on the left, or if the picture looked like the thing on the right, what I measure in terms of the entries of this matrix would be completely different. The entries would all be mixed up. And that would have been a nightmare. So we decided not to do that. So the community decided to order the mass eigenstates in this way. And the side effect of that is that the difference between m2 squared and m1 squared is always a positive number. But the difference between m3 squared and m1 squared is a positive number in this case, and it's a negative number in that case. So that means that every time you do a physics experiment, you have to remember that delta m squared 3, 1 is either positive or negative, and that's an observable. You can measure the sign, you know, plus or minus sign of this delta m squared 3, 1. Okay? And I know this sounds silly, but it's very important. And again, this is all a matter of convention. There's a lot of other fun stuff, so if you really like this sort of thing, which very few people do, but if you like this sort of thing, there's another fun exercise you can ask yourself, which is, so now that I've gone through all this thing of defining these mass eigenstates, what's the physics range of these mixing angles? You know, I always talk about, you know, tangent squared of a mixing angle, tangent squared of a mixing angle, or sine of a mixing angle. So can I have a negative mixing angle? Does this mean anything? The answer is no, you can't, and it doesn't mean anything. Can I have a mixing angle that's bigger than pi over 2 or less than pi over 2? You also don't need to do that. You can pick the mixing angle to be between 0 and 90 degrees. And then what's the physics range of this CP odd phase delta? And the answer is it depends. You can pick whatever you like. You can pick it to be from 0 to 2 pi, in which case you should consider values of this mixing angle which have a negative sign, plus, you know, sine or cosine. Or you can pick this to go from 0 to 2 pi, and then this sine of theta 1, 3 is a positive definite number, for example. So there's a lot of time you can waste figuring out what's the range of these mixing angles. We've actually done that. I have a paper on this, which is why I talk about it. It's a lot of fun. And in the quark sector, people didn't care about this so much because it turned out that all the mixing angles were really small, so none of this was a big question. In the neutrino sector, it's kind of more fun, and you can think about it that way. Okay, so now that we've gotten here, let me tell you how to take the information that we learned from the 2-flavor mixing and apply it to the 3-flavor mixing. And what happens is that we got lucky 2 times in order to understand everything in terms of 2-flavor mixing. We got lucky for 2 reasons. One is, one delta m squared is way bigger than the other. What this means is, in the case of the atmospheric neutrinos, if you look at the values of L and E that you have available for the atmospheric neutrinos, the small delta m squared is too small. That means that if you do delta m squared 1, 2 times L over E for the atmospheric neutrinos, that number is always too small. So that means that that oscillation never turns on. And let me find a picture of something useful here. So that means you have a system that, these are the mass eigenstates. If you can't resolve this difference here, then this looks like a two-flavor system. And that's what's happening with the atmospheric neutrino problem. And basically, when you do that, the atmospheric neutrino analysis effectively measures this mixing angle over here. So that's the mixing angle that sine squared is 1/2, tangent squared is 1. That's what we call a maximal mixing angle. Now, it also turns out, and we also got lucky that way in some sense, that if you look at this row here of the mixing matrix, this entry here is actually quite small. So every time you're doing an experiment that involves only electron neutrinos, if you can neglect that this entry here is non-zero, then you effectively have a two-flavor problem again. So this is also contained in this picture here, and this is what I'll probably talk about the next time. So if you look at these colors over here, you notice that these colors represent the different compositions of my states, and I'll talk about that in more detail. This component here is really small. That means every time I'm doing something that involves this red flavor, the electron neutrino, I can pretend like this flavor doesn't exist, this mass state doesn't exist, so I only do a two-flavor problem. So with that, that means everything that I said about two flavors for the solar neutrinos can be applied here directly. And it turns out that the solar mixing angle has to do with these two entries of the matrix here, so they constrain this other mixing angle here, 1, 2. Okay? So finally, the last thing which I want to mention, I think I'm running out of time, right? Does that sound right? Can people confirm? That watches, we started a little bit late. But the last question that it took a long time to address was, remember I said that this entry here turns out to be very small, but it doesn't have to be 0. So what's nice is I can do an experiment where I can look for electron neutrino disappearance in a value of L over E where the solar delta m squared doesn't matter. Okay, so if I do that experiment, that again is in a situation where the baseline is short enough that I only get to see, these two pairs here converge into one. They look like one particle as far as my oscillation experiment is concerned. Then I should be able to see the oscillation of the electron neutrinos with this a small wavelength solution, or the large delta m squared solution. And that was the last thing that we did. And I'm ashamed to say that I think I don't have the data for that. But I can talk about it next time. But this is that I wrote down over here. It turns out, so this is a big achievement. And I do want to say this. While people were building this stuff up, it was not clear that this was correct or not. There were a bunch of competing solutions, and this was getting to look better and better. But what's interesting is you could make a prediction. You should say, hey, we should be able to see oscillations of electron neutrinos with this fast oscillation here, with the fast oscillation here as well. Because we know what the oscillation length is supposed to be, we can set up an experiment to do that. That was actually a combination of 3 experiments: the Diabé experiment, the Reno experiment, and the double show experiment. And those 3 experiments were set up because we knew what the oscillation wavelength was supposed to be. We just didn't know what the amplitude of the oscillation was supposed to be. We only knew it was going to be small. So we did that experiment, and we saw a non-zero effect associated with a mixing angle which is about 2% for the mixing angle squared. And that's the value of this angle over here. Okay? So I think I'm going to stop here. What I want to do next is to 2 things. One is to take advantage of this picture that we've just designed to tell you what it is that we don't know yet. And that's one big area of experimental research right now, which is to say, let's pretend that this picture is actually correct. What is it about the phenomenon that we haven't measured yet? And then I'll spend the rest of the time talking about models as well. So I think that's the plan. So I'll stop here. It's okay.